Good morning, everyone. We are Group 1. We will now begin our presentation. First, let's look at the definition. Let's define our terms. Thermodynamics comes from the Greek root term meaning heat and dynamics meaning power or force. Simply put, thermodynamics studies the relationship between heat, work, and energy, and how energy is transformed from one form to another within a physical system. Understanding this concept is key to analyzing everything from an engine efficiency to chemical processes.
So hi, Assalamualaikum, and I'm Taufik. So right now I'll be continuing with the system. So here we got the definition of a system. So what is system? System is really refers to the specific part of the universe we choose to study, and everything outside the boundary is called the surroundings. So here we just think of it like we drawing an imaginary boundary around something. So inside the boundary is we call system and outside we call surroundings. That is definition of a system. So the next slide is, so right now we have three systems. The first one open system, second one closed system, and the third one is isolated system. Okay, for the open system, easy definition for the open system is the systems that lets both matter and energy to go in and out. For example, the open system is a boiling pot of water without a lid. The steam can escape, but the heat also enters from the stove. So here, both matter and energy go move in and out. That is open system. Okay, so for the closed system, a system that allows only energy to enter or leave, but not matter. So the example for closed system is a sealed bottle of water. No water can escape, but the bottle can heat up or heat down. So here the matter stay, but the energy move. In simple words, the energy can move, but the matter stay inside. Okay, so the last one is isolated system. Isolated system is a system that does not allow matter or energy to enter or leave. The easy example is for the thermos, a perfect thermoflask. The thermoflask is there is no heat can come in and can go out. Also, there is no matter can go in and go out. So, in simple words, we can say the nothing goes in and nothing goes out, not even the heat. That's all.
So in this slide, I will talk about thermodynamics equilibrium. Thermodynamic equilibrium is a state in which a system's microscopic properties like temperature, pressure, and volume remain constant over time, and there is no net exchange of energy or matter with its surroundings. It is a condition where no changes occurs in the system over time. Next, I will talk about zeroth law of thermodynamics. If a system are each in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. This principle is the foundation for measuring temperature as it defines the concept of thermal equilibrium as transitive. So in the diagram below, you can have a better understanding in the relationship between the three objects. So there are different types of temperatures. For example, Celsius temperature, Fahrenheit temperature, and absolute temperature. The absolute temperature is a measure of temperature starting from absolute zero, the theoretical point where particles have minimal thermal motion. It is measured on absolute scale like Kelvin. 0 Kelvin will be absolute zero, which is equivalent to negative 273.15 degrees Celsius. So for degrees Celsius to convert to Kelvin, you have to plus 273.15. There is also an equation below which tells you how to convert degrees Celsius to Fahrenheit. Here is an example of heating treatment of steel. So when steel is heated and then rapidly cooled, quenching, its microstructure it changes, which increase its strength.
Hi, my name is Yeje and I'm going to talk about pressure. Pressure is the force applied perpendicular, which is 90 degrees, to the surface per unit area. Pressure is also a key state variable that influences a system's energy and its behavior. Pressure is a scalar quantity, and here is the formula for the pressure. P equals to force divided by area. In SI units is PA equals to Newton divided by meter square, and it can also be written as this. Here is an example, the deep sea environment. At great ocean depths, the high pressure compresses gas and carbon dioxide that normally would be gaseous at atmospheric pressure, but here at great ocean depth, the high pressure can compress these gases in and make them exist in liquid form. Next is phase graph. If a system are each in thermal equilibrium with the third system, they are also in thermal equilibrium with each other. What does this mean? It means that, let's say, system A is thermal equilibrium with system C, then and system B are thermal equilibrium with system C, then hence system A and system B are thermal equilibrium. This principle is the foundation for measuring temperature, as it defines the concept of thermal equilibrium as transitive. Last, this is the phase graph. There are two equilibrium, one critical point and one triple point in this graph. That's all for me.
So guys, my name is Lutfi and I will continue this presentation. So here we have a phase change graph for water, which is a perfect example to illustrate these energy concepts. On the y-axis, we have the temperature, and on the x-axis, we have the energy added to the system. Notice that when we add energy, the temperature of the solid ice increases steadily until we hit the first flat plateau. This is the phase change from solid to liquid. Here, the energy we are adding isn't increasing the temperature, but it is being used to break the molecular bonds to melt the ice. This specific energy is called heat. The heat of fusion, which is for water, is 6.01 kilojoule per mole. Once all ice is melted, the temperature of the liquid water begins to rise again until we hit the second plateau. This is the phase change from liquid to gas. Again, the temperature stays constant while the energy we add works to overcome the forces holding the water molecule together. This energy is the heat of vaporization, a much larger 40.65 kilojoule per mole for water. So this graph clearly shows that during phase change, the energy input changes the substance state, not its temperature. So next, we have a phase change diagram. This diagram introduces the different type of phase changes or how make the transition between solid, liquid, and gas. You will see a classic diagram here. For example, melting is the transition from a solid to a liquid, and freezing is the reverse. Vaporization turns a liquid into a gas, and condensation turns a gas back into liquid. And ionization turns gas into plasma, and recombination turns the plasma into gas. A particular interesting one is sublimation, which is it directly change the solid into a gas without becoming a liquid. Next, we will go through the one of example of sublimation of dry ice. Dry ice is solid carbon dioxide or CO2 at normal atmospheric pressure. It doesn't melt into a liquid, but it undergoes sublimation, turning directly from a solid into that cool fog-like gas we often see at concert or in science labs. Fun fact here, at the incredibly high pressure found in the deep ocean, the behavior of CO2 changes completely. The pressure is so great that it can actually compress the gas into a liquid form, which wouldn't be possible at the surface. This perfectly illustrates how pressure and temperature are both critical in determining the state of matter. So next, we will move to the next slide, which is ideal gas. So what is an ideal gas? In simple terms, it is a theoretical gas that makes our calculation much easier. It has two key characteristics. The first one is the interatomic forces between the gas atom or molecules are extremely weak. For all particular purposes, we consider them to be zero. They don't really attract or repel each other. And the second one, the volume of the gas atom themselves is negligible. This means the gas simply expands to fill whatever container it is in, and its volume is entirely determined by the size of its container. Although this model is simplified, it works remarkably well for many common gases like nitrogen and oxygen under normal conditions. So I will pass to my next roommate for continue this discussion. Thank you.
Now, let's talk about gas law. First, we have the three laws. This is Boyle's law, Charles's law, and Gay-Lussac's law. But there's a simple way to understand all of them by only using an upside-down triangle. Inside the triangle, we have the three main variables, which is P, pressure, V, volume, and the last one is T, temperature. The trick is, the variables on the same label are inversely proportional and vice versa. To identify the gas law, just cover the variable that stays constant. For example, if I want to know what Charles's law says, I cover the P, pressure, because pressure is constant. Now, what I'm left is with V and T, which tells me that volume is directly proportional to temperature. So as temperature increases, volume increases. Now, if you want all the variables in one single formula, we can use an equation that's called ideal gas equation, where it states P V equals to nRT, where P is equals to pressure, V is volume, N is number of moles, R is gas constant, and T is temperature. This equation links pressure, volume, temperature, and the amount of gas all at once. So how do we find the number of moles? N. There are three ways. The first one is from the mass, second one is from the number of particles, and the third one is from the volume of gas. Once you know the N, you can use this equation to solve any missing variable.
Okay, so right now we continue with the tutorial question. So the question number one is, what is the zeroth law of thermodynamics? So we go to the next slide. So here, as you can see, the zeroth law of thermodynamics is the mean is if object A has the same temperature as object B, and object B has the same temperature as object C, then A and C also have the same temperature, same equilibrium. So the super simple example for you guys to easy to understand the zeroth law of thermodynamics is, okay, so here you hold a thermometer B to a cup of hot water A until both have the same temperature. And then you took the thermometer B, you put it into the another cup, which is C. And then if the thermometer shows the same reading, it means then cup A and cup C have the same temperature. If the thermometer just now show the same reading, which is same reading with the cup A, and then cup A and cup C have the same temperature, even without touching each other. Without the cup A doesn't touching with the cup C. That's all.
Hello everyone, I'm Eugene, and now I'll be continuing onwards with the tutorial. So let's move on to question 2, which asks, based on the diagram above, define the critical point of a substance as well as the triple point of a substance. And here we see a phase diagram, which, as you have learned in the lecture just now, shows the 3 states of a substance: the solid, liquid, and gaseous state. And you can see that the critical point is actually located at the top right of the phase diagram between the liquid and gas phase boundaries, whereas the triple point is located down in the lower left corner, intersecting the solid, liquid, and gas points. So as you probably would have known, the critical point is actually a point on the pressure temperature graph representing the end of the liquid gas phase boundary. So what this means is that above this temperature and pressure, the boundaries between liquid and gas start to fade, and the substance begins to act as a supercritical fluid. On the other hand, the triple point of the substance here is a point where all 3 phases of the substance is allowed to coexist with each other in thermodynamic equilibrium. Now let's move on to the third question, which says, which of the 2 PT graphs shown in the image represents the phase diagram of water? Explain your reasoning. And you can see that between these 2 PT graphs, one has a negative gradient, so it is sloping to the left, while the other one has a positive gradient, it's sloping towards the right. So you may recall during your secondary school studies that water is actually unique among most substances in that as the pressure increases, so going up the y-axis, its freezing point decreases. So as you can see, the x-axis or temperature goes towards the left. And as a result, the solid liquid phase boundary for water has a negative gradient, sloping towards the left. And so the left graph is the correct one that represents water. This is something that is quite helpful because when you see this graph, you know that it is most probably water. Because for most other substances, as the pressure increases, its freezing point actually increases, which means that it requires a higher temperature to freeze. So let's go on to the 4th question, which asks, what is the pressure of neon gas inside a container having 10 to the power of 17 molecules per centimeter cube at room temperature, where room temperature given here is 300 Kelvin. For this question, you can actually just use the ideal gas law because we are given the number of molecules per unit volume as well as the temperature. Now what we can do is rearrange the ideal gas law equation such that we move the volume over to the right side, and we can substitute n, the number of moles, with the number of moles divided by Avogadro's number. And what you can notice here is that we have R, the ideal gas constant, dividing with the Avogadro's number, which actually gives the Boltzmann constant, denoted here as K subscript B. So once we do that, we can actually just substitute the values of number of molecules per unit volume, 10 to the power of 17, and don't forget to multiply with 10 to the power of 6 due to the fact that the unit here is given as centimeter cube instead of meter cube. And once we do the calculations, we get 414 pascals. And for the last question, Consider a volume of monoatomic gas. The gas is in a state where the number of molecules per unit volume is 2.4 times 10 to the power of 25 molecules per meter cube. The effective radius of a single gas atom is 1.82 times 10 to the power of negative 10 meters. Calculate the mean free path of a gas atom. And if you recall from the lesson earlier, we can actually just use the formula for the mean free path of gas atom. So all we have to do is substitute this value, the number of molecules per unit volume, as well as the diameter, which is double of the radius given here. And we find that the mean free path is actually just 7.078 times 10 to the power of negative 8 meters.